Hi everybody. So I am going to try to address a couple of the questions that some of you had from your classwork 12. And I'll hopefully be able to answer some more questions that might pop up that people have been sending me. One of the things that I'm going to do is I'm also in this video going to quickly go over a practice question associated with some of the questions that people ask, but maybe that wasn't quite what they were asking, but I think I know what people are asking. And then I'm gonna address a couple of questions that I saw a couple of times. So the first thing is, just so you can see, I don't know if you can see, but my t-shirt says something about green chemistry, and green is the new element, or is the most important element in chemistry. This is your reminder to please go and sign up for your green chemistry projects. I actually just gave a workshop on green chemistry to faculty, students, and different companies. And one of the companies is Dow Pharmaceuticals, and they're really interested in getting students learning about green chemistry so they can hire people. They're really only looking for people who have green chemistry backgrounds. But anyway, back to what we were doing. So one of the questions was, how do I identify an addition versus an elimination reaction? Now, if the question really is, how do I know will a reaction do an addition, or how will I know if it will do a substitution, I'll talk about in a second, but that's actually in the next classwork. But how do I identify whether something did an elimination or a substitution? Let's say I had this molecule and you were given this as a product. Because I replaced the bromine with a chlorine, that means we had a substitution. And so one of the other questions was, for this substitution reaction, do you get one product or two products? That's actually a great question. So if I were to use Cl- to replace the bromine, yes, you would get two products, but we oftentimes don't really focus too much on the other product, the Br-, because we oftentimes, when we do our workup for a reaction, which means this, after you've done the reaction, how do we get it pure and get our pure compound? We oftentimes get rid of the bromine. So yes, there will always be two products. If I start with two for the substitution, I'm going to end with two products. If I started with my molecule and I ended up making a double bond, that means I had to have an elimination. So substitution is a replacement of the leaving group, and elimination is the removal of the leaving group and a beta hydrogen. So just to recall, where the leaving group is called the alpha position, and so we're going to remove any hydrogen that's next door. So in the next classwork, you'll talk about a couple of beta positions. So all of these, I'm not drawing in all the hydrogens, but all of these next door to the carbon right next door is beta. And so depending on which one you remove, so if I remove this first one that I just put a star next to it, that would have given me this product. If I remove the one with the smiley face next to it, I would have gotten this product. But essentially what I'm doing, and I'm going to do some erasing. I'm essentially removing the leaving group, removing the hydrogen, taking electrons from the bond between the carbon and the oxygen to make a double bond here, and taking the electrons in the bond from the bromine and putting them as a leaving group onto your molecule. And so elimination reactions require a base, but you're going to see in the next classwork that our elimination reactions are can use bases that are different sizes and different types, and very often bases can act as nucleophiles. Remember, we talked about Lewis bases are also considered nucleophiles, but when we talk about bases, we're really specifically from here on out talking about the thing that's going to remove a hydrogen. When we talk about nucleophile, we're really talking about that thing that's actually reacting with an electrophilic center. So that's how we're going to define it. So the base is going to remove a hydrogen. And so in elimination reactions, we define the reagent that's used as a base because it's going to remove a hydrogen, and the substitution, we define the substance as a nucleophile. Now, some of our nucleophiles are better than others, and that was part of what your classwork was about. And one of the things that people asked me about, and I'll talk about that in a second. So, other than identifying, if you get a double bond, you have to remove two things to get to the double bond. And for a substitution, you're replacing a group. So in one of your questions, you had something that had a leaving group that looks something like this. And you had a nucleophile. It was something like this. It wasn't quite this. And the nucleophile attacked the electrophilic center. That's the center that's next to the leaving group. This whole thing is the leaving group. And a couple of you made this mistake. The leaving group is going to leave and take the electrons with it. So the leaving group takes the electrons. So the OH is going to bond to that carbon. Since carbon already has a full octet, it needs to lose some electrons, and so the arrow goes to the leaving group. Some of you were drawing the arrow the other way. This is the correct way to do that. All right, so one of the other questions had to do with the strength of the nucleophile and how do you know kind of that. And that is actually a good question. It's a good practice question. Now, there was a chart that you had, and most of the things on the chart had to do with arrow. So for example, nucleophiles want to share electrons. So something that has a lone pair that doesn't want to have that lone pair or that negative charge is going to be a very strong nucleophile. So all of these things are carbons with negative charges. They don't want to have those negative charges. On the other hand, if you had something like, this is called ethoxide, if you had something like this, that's not as strong. So it's a good nucleophile, but it is not as strong because oxygen does like to have negative charge compared to carbon. But if I had something like this is diethyl ether. And diethyl ether has no charge on it, so it's already neutral. Since it already has this octet, it's neutral. It would prefer not to lose any of those electrons to become positive, so this is going to be a poor nucleophile. So the rate of the reaction is going to improve if I have a stronger or better nucleophile. If my leaving group is good, if my substrate will react in that type of reaction. So for example, in a SN1, an SN1 needs a carbocation to form, and because it needs a carbocation to form, we're going to be primarily seeing things that are like tertiary carbocations forming, secondary, allylic or benzylic. Those are the more stable. Actually, allylic and benzylic are the best. For SN2, the better substrates, the faster ones are going to be methyl, primary, and secondary. So those were some of the main questions that people asked in your classwork. One other question that was asked about is just practicing these problems. There's quite a few of them in your textbook, and I would recommend them. There's going to be some in the next classwork, but I can definitely put together some examples, as well as I'm going to set a time for our practice session that I'll post soon, and so you can, if you haven't already, watch this after I posted, and then you can take a look. And I'm still grading the classwork, but if some other bigger things come up, I'll make another video.